Hey there, science fans! Ever wondered how a tiny water droplet holds itself together, or why you can smell freshly baked cookies from a distance? The answer lies in the fascinating world of intermolecular forces. These invisible bonds influence everything from the state of matter to the properties of liquids. Think about water for a moment. It can exist as ice, liquid water, or steam, thanks to intermolecular forces. In ice, water molecules are locked in a tight embrace, while in liquid water they move more freely. And in steam, the molecules are far apart and zipping around like popcorn in a hot pan. So buckle up, science explorers, as we delve into the amazing world of intermolecular forces and discover the secrets behind these incredible phenomena. Now let's break down these invisible forces that are constantly at play around us. These forces play such a big role in our world, influencing everything from the state of matter to the properties of substances. There are three main types of intermolecular forces that we need to understand. These are dispersion forces, dipole-dipole forces, and hydrogen bonds. First up, we have dispersion forces, also known as London dispersion forces. These are the weakest of the three. These forces exist between all molecules, whether they're polar or non-polar, and are caused by the movement of electrons. Electrons are constantly zooming around the nucleus of an atom, and sometimes they create a temporary dipole. This temporary dipole can then induce a dipole in a neighboring molecule, leading to a weak attraction between them. Next, we have dipole-dipole forces, which occur between polar molecules that have a permanent dipole. These opposite charges attract each other, just like magnets do, creating a stronger bond than dispersion forces. Finally, we have hydrogen bonds, which are the strongest type of intermolecular force. Hydrogen bonds occur when a hydrogen atom is bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine. These strong dipoles can then form hydrogen bonds with other molecules, resulting in a very strong attraction that significantly affects the properties of substances. Intermolecular forces play a crucial role in determining the states of matter. These forces are the invisible glue that holds molecules together, influencing how they behave in different environments. Solid, liquid, gas, and plasma. Each state has unique characteristics based on the strength of these forces. In a solid, molecules are packed tightly together like sardines in a can. This close packing is due to the strong intermolecular forces that act like a powerful magnet. The intermolecular forces are strong enough to hold the molecules in a fixed position, giving solids a definite shape and volume. This rigidity is what makes solids hard, and often difficult to compress. In a liquid, molecules have more freedom to move around, like cars navigating a busy city street. They are not as tightly bound as in solids, allowing them to slide past one another. The intermolecular forces are weaker than in a solid, allowing liquids to flow and take the shape of their container. This fluidity is why liquids can be poured and can conform to the shape of any vessel they are in. In a gas, molecules are far apart and move around rapidly, like kids running around a playground. This high energy and low interaction make gases expand to fill any available space. The intermolecular forces are very weak, so gases have no fixed shape or volume. They are easily compressible and can spread out indefinitely. Plasma, the fourth state of matter, is like a superheated gas where atoms have been stripped of some of their electrons. This ionization gives plasma unique properties, such as conducting electricity and being affected by magnetic fields. Temperature plays a key role in determining the state of matter. As temperature increases or decreases, it can cause matter to transition from one state to another, such as ice melting into water or water evaporating into steam. Section 4. Molecules on the move. The Kinetic Molecular Theory. To understand how matter behaves, we need to talk about the Kinetic Molecular Theory. This theory is fundamental in explaining the properties and behaviors of gases, which are all around us. This theory helps explain the behavior of gases by focusing on the movement of molecules. It provides a framework for understanding how gases respond to changes in temperature, pressure, and volume. Imagine a room full of bouncy balls constantly bouncing off each other and the walls. This is a great analogy for how gas molecules behave in a container. That's kind of like how gas molecules behave. They are in a state of perpetual motion, always moving and colliding. The kinetic molecular theory states that gas molecules are in constant random motion, colliding with each other and the walls of their container. These collisions are what give gases their unique properties. The speed of these molecules is related to temperature. As the temperature increases, the molecules move faster. Higher temperatures mean faster moving molecules, just like how a hotter oven makes popcorn pop faster. This is a direct result of the increased energy in the system. Pressure, another important gas property, is caused by the force of these collisions. When molecules hit the walls of their container, they exert a force, which we measure as pressure. The kinetic molecular theory helps explain why gases behave the way they do. It provides a comprehensive understanding of the relationship between molecular motion, temperature, and pressure. Section 5. The wonders of liquids. Surface tension, viscosity, and capillary action. Liquids have some pretty cool properties of their own, thanks to intermolecular forces. Surface tension is like an invisible skin on the surface of a liquid. It's caused by the inward pull of molecules at the surface. This is why small insects can walk on water and why water droplets form spherical shapes. Viscosity is a measure of a liquid's resistance to flow. Think of honey. It's very viscous and flows slowly. Capillary action is the ability of a liquid to flow in narrow spaces against the force of gravity. This happens because of the interplay between cohesive forces and adhesive forces. Section 6. Dissolving the mystery solutions and solubility. Let's talk about solutions. Those magical mixtures where one substance dissolves completely into another. The key to understanding solutions lies in the concept of solubility, the ability of one substance to dissolve in another. Think of dissolving sugar in water. Water is a polar molecule, meaning it has a slightly positive end and a slightly negative end. Sugar is also polar, so the positive and negative ends of the water molecules attract the positive and negative ends of the sugar molecules. This attraction overcomes the forces holding the sugar molecules together, causing the sugar to dissolve. But what about oil and water? Oil is a non-polar molecule, meaning it doesn't have distinct positive and negative ends. Section 7. Intermolecular forces in action, everyday applications. Intermolecular forces might seem like a microscopic concept, but they have a huge impact on our everyday lives. From the food we eat to the clothes we wear, these unseen forces are constantly at play. Take cooking, for example. The process of boiling water, baking a cake, or even just melting butter all rely on intermolecular forces. Heating these substances weakens the forces holding the molecules together, allowing them to change state and transform into delicious treats. Intermolecular forces are also essential for many adhesives like glue and tape. Even our DNA, the blueprint of life itself, relies on intermolecular forces.